In this video, I'm continuing the free body diagram series. Here we'll be doing several examples of just several different varieties of these dynamics problems, all of which are easy to understand if you draw the proper free body diagram, and very difficult to understand if you don't, or if you either refuse to draw it or you draw it incorrectly. So here's one in front of us. Let's read it. Two boxes are sitting on the floor of an elevator as shown. The elevator is moving up but is slowing in preparation to stop. If the top box presses down with a force of 40 newtons, what is the acceleration of the elevator, and what force is being applied to the floor by the bottom box? Well, we got a picture here that I went ahead and colored one green and one red just to kind of make life a little simpler on us. And before running the video, I created the free body diagrams. They're just, don't read anything into the fact they're not the same level. That's just where I drew them. This is the forces acting on the top box, the green box. Obviously, its weight, gravity's acting on it, so its weight is pulling it down. WG, that's gravity acting on it. The other thing acting on it is the 3 kilogram box, the red box, is pushing up on it. So I have a vector going up. That is the normal force from R on G, red pushing on green. Now the bottom box, it's kind of a similar situation. Its weight, the weight of red, is pushing down. There is a normal force of the elevator pushing back up on the red. That's right here at the floor that's happening. But then there is this third force acting on it, and that's the normal force from G pushing on red. This green box is sitting on top of the red box, and it is pushing down. Actually, this force, if there's no acceleration, that force would be equal to its gravity, just pushing out the gravity of the green box. Nonetheless, that's the situation. As always, if you understand the free body diagram, then you understand everything difficult about the problem. I'm going to solve this one. Looks easier to solve, so I'm going to start with it. And as always, I start with Newton's second law. We then populate the left side of that based on what the free body diagram said to us. Left side says the normal force of red pushing on green minus the weight of green. Notice how the subscript green is in both of those. These are forces acting on it. All of that is equal to the right side, which we do not get from the free body diagram. We get from either the picture or somewhere in the text of the problem. Those forces will cause that mass, the 5 kilogram green mass, to have a certain acceleration. Plugging in what we know, the 40 newtons, that's what we were told in the problem, that it was pushing down with a force of 40 newtons. That would be the normal force of R on G. Now, I need to point out that it says if the top box presses down with a force of 40 newtons, if green is pressing on red with 40 newtons, then thanks to Newton's third law, red is pushing on green. So while the box referred to green pushing on red, the problem rather referred to this particular item. Because these are a Newton pair, we could just apply it to this item. So that's 40 newtons minus the weight of the green box, 5 kilograms times 10 meters per second squared is 50 newtons. All of that is going to make the 5 kilogram box have a certain acceleration. Well, it's just a matter of doing that math now. Left side works out to negative 10. Right side is 5 kilograms times A. When you solve for A, you get that the acceleration is negative 2. Now, I didn't have to force that negative. It became a negative. What that means is it said the elevator was moving up. We kind of subtly in all that, we picked the up as the positive direction. I say that this force vector here is that force vector there, and it is pointing up. And since there's not a minus sign in front of it, that is, there's an implied positive sign, that means that we've made up positive. And so the problem said it was slowing, ready to stop. Well, if you're moving up and you're slowing, that's an acceleration backwards, downward as a matter of fact. So the acceleration came out to negative 2 meters per second squared. Okay, we were asked to find two things. The acceleration of the elevator, we did that, and now the force being applied to the floor by the bottom box. Well, the same thing. Newton's third law tells me that if the red box is applying a force to the floor, then the floor is applying the exact same force to the red box. So that would be, we were asked to find the normal force of red on elevator, we're actually going to find the normal force of elevator on red, and that's going to be good enough. Let me just get it all up here, right there. As always, we write Newton's second law. We then populate it based on the free body diagram. Let's look at that in some detail. We've got the positive one is up, elevator on red. We have minus the normal force of the green pushing on the red, and the normal force of the, excuse me, not normal force, the weight of red. Both of those are negative, so that's what we put there. Again, right side comes from someplace other than the free body diagram. Since this is the one that we don't know, I'm going to isolate for it, and then I plug in the numbers. The mass, these are the forces acting on the 3 kilogram mass, so that's the mass we use. We plug in the acceleration, negative acceleration that we found in the previous step, plus the force of green on red. You remember that we calculated red on green, but Newton's law tells us what green on red is. Well, in the problem said green on red too. That's the 40. Plus the weight of the red is 30 newtons. That's hidden behind that box, and I don't suppose I can fix that right now. And so this is minus 6 newtons plus 40 plus 30, and that's 64 newtons. And that is the force that it pushes down on the floor with. You'll notice that if you just look at this, add these together, 8 kilograms, so it would normally push down on the floor with 80 newtons of force. The reason it's pushing down with less is because the elevator itself is having negative acceleration, so that makes the boxes not push quite so hard down on them. As a matter of fact, that negative acceleration was a really big number. You would expect, that is, if the elevator stopped rather abruptly, you would expect these boxes to fly up in the air, and indeed that would be what happened.